Good morning, everyone. My name is Jiangchuan Huang. I'm a data scientist at ConocoPhillips. Today, I'm going to talk about forecasting the future of oil and gas supply. This is a joint work with my colleagues, Darryl Buswell and James Pearson. Darryl Buswell is also a data scientist at ConocoPhillips, and James Pearson is an economist at ConocoPhillips. So the objective here is to forecast the US oil and gas supply with user input or scenarios. For example, if you are an economist or executive of an oil company, you're always facing the question of, if my rigs increase by 3% every year, what would the production be in the future? Or under a scenario such as, because of progress of technology, if my drill time decreased by 1%, my initial production of a single well increased by 3% every year, what would the production be? So here we have the actual production or historical production, and we want to have the forecast under certain scenarios. In order to answer this question, we connected three kinds of data: the rig count, well description, and production. So the rig count gives you where the rigs are, what's the types of the rigs. And the well description gives you the location and the well types and the spud date and first production date of a well. So the spud date is when a rig began to drill a well, and the first production date is when a well began to produce. We also have the production data. It tells us the production, oil and gas production of every single well for every date. Here gave a taste of what's the number of rigs look like. We have two kinds of sources from Baker Hughes and Drilling Info. You can see that the number of rigs increased and peaks around 2014 when the price was high, and then there was downturn and the number of rigs declined, and it reached the bottom around 2016 and increased again. So in order to do the forecast, we do Monte Carlo simulation to try to simulate what's really happening in the oil field. And our model have two parts. One is from the number of rigs to the number of wells. The second part is from the number of wells to the production. Let's first look at the first part. The first part is when the rigs arrive, it might spend some time drilling, for example, 1 month. After finished drilling, it will go straight to completion. It might spend another month complete, and then after that, it began to produce. And of course, the production of a well always have this decline shape. So basically, if you model the production of every single well, and you already know the number of wells that are producing every month, you aggregate them, you get the total production. But sometimes, for example, when the price is low, after finished drilling, we might, instead of go immediately to completion, we might instead put it in inventory. We call this the drilled but uncompleted backlog. So the wells might idle here, for example, for 1 year when the price is low. And then later, when the price is higher again, we might decide to bring it back. We call that to burn the inventory. And then at this stage, it would go straight to completion, maybe for another month, and begin to produce. So to increase the production, we can either, for example, increase the rigs, or decrease the drill time, or decrease the completion time. Or we can quickly bring those wells that's already in inventory back for completion. That would provide a burst of production for us. And so if you look at that data set, some of the wells might say that it's drilled but not producing. So it can be because it's still in this completion time, or it's actually it's idling. Right? So our models separate the well into two categories. One is the normal wells, as drill and then complete and produce. The second one is drill, and maybe the economy is not very good. We send it to inventory, so it idles for some time, for example, for 1 year, and then bring it back for completion and produce again. So these two kinds of wells would create two different backlog or inventory. One is from the normal well, if it's still in completion. There's some well that's drilled but not producing. Or if it's actually idling, and that's drilled but not producing. So once we figure out the number of wells for every month, we can simply model the production of a single well. So we know that no well will produce forever. So the well will always decline as time goes on. So we use opposite equation to model the production of a well. So opposite equation is an equation by three parameters. The Q is the initial production. B and D controls how fast the well production declines. The opposite equation can take one of those three forms. Depending on the value of the B, it can take exponential, hyperbolic, or harmonic forms. So we have the number of wells, and then we also have the production for every single well. Now it's time to do the forecast. In order to do that, we separate the wells into three categories: the old wells, middle wells, and future wells, by using those three dates. The start date is when we start simulating our model, the current date, and also the end date is how fast you want to forecast onto. The old wells are the wells that have first production date before 2012, before the start date. And middle wells have the first production date between start date and current date. And future wells would be the well that has first production date after current date. So let's first have a look at the old wells. So for the old wells, they have already been producing since this starting date. So we can simply aggregate them and then fit it with the opposite equation. And that would be, the blue would be our forecast to the future for the old wells. And for the middle wells, it's a little bit more complicated because now the wells starts producing at different times. In that case, instead of aggregating them first, we just fit each single well with the opposite equation and then aggregate them. We get the forecast of the future for the middle wells. And now comes the future wells. Since when we're fitting the historical wells, we already get some initial production and also the decline rate. And we also know how many wells began to produce at every single month by running the Monte Carlo simulation. Now we can just generate those wells by using the initial production and then the decline rate we got from historical wells. And if we aggregate them, we get the total production of future wells. So if we put all of the three together, you can see the oil production and gas production. Let's first have a look at the oil production. So the first panel is all the wells, the actual historical data and its forecast. The second one is the actual and the forecast for the middle wells. The third one is our generated future wells. So if you sum up all those three, you get the total. That would be the actual forecast, actual production and our forecast. Likewise, you can do similar things for gas. So here, the forecast depends on the scenario. For example, it depends on your expectation of number of rigs in the future, or how long does it take to drill a well? Will the drill time decrease in the future because progress of technology? So at this stage, we're able to answer the questions such as if you increase your rig by 3%, how would your production be in 10 years? Of course, we can run this for different well types. For example, we have the tight oil well, tight gas well, conventional oil well, and conventional gas well. So the tight here means unconventional. So unconventional oil well and unconventional gas well. And each well can produce both oil and gas for each of the types. And you can partially aggregate them. For example, if you aggregate those to oil, you get the tight oil production. or the tight gas production or conventional oil production. You can further aggregate them to get the total oil and gas production. Of course, we can also do this for different occasions. For example, if you are only interested in Alaska production, you can run this for Alaska only. Or if you are only interested in Permian Basin only, you can just run this for Permian Basin. So in that case, we know the total production and also in different well categories and also in different locations. So to conclude, so we use Monte Carlo simulation is a very good model to forecast the oil and gas production for a given scenario. So unlike a pure machine learning model where the model is a black box, Monte Carlo simulation enables us to incorporate our domain knowledge into the simulation with great details. The scenario parameters such as the rig count, drill time, inertial production from Monte Carlo simulation all have a physical meaning. This enables the economists to design a scenario strategy based on those parameters. So by doing Monte Carlo simulation, we not only know what the future production be, and we know what factor cause the future production increase or decrease. Is it because of increase of rig count or decrease of drill time or increase of inertial production? And that's very important for our economists and executives of oil companies so that they can understand what's really going on in the oil field and how the change in the oil field can affect production in long term. And that can can help them to do long-term decisions. So here's the reference of the opposite equation. Thank you.
Do we have time for 1 or 2 questions?
Hi, were you able to backtest these results to see if your predictions would have been accurate for the last 10 years?
Yes, we can. So basically from the slide, you can see there's the current date. So basically if you set your current date, pretend your current date to be like 1 year before, and then you will be able to backtest. Actually, our economists call it calibrate because they actually have control on some of the input parameters. For example, if they think the production is a little bit lower, they might think, oh, maybe my assumption about the rigs is not correct. Maybe I should increase my rigs by 1%. So it's not a pure forecast model. It's actually a model that gives you production based on your given scenarios. Yeah.
We can take one more question here.
In your Monte Carlo simulations, is one of your inputs the type curve for the area as well? Like, are you presuming that those wells have specific production profile and they are going to be operated under certain circumstances, like when it comes to choke and all that? Because that controls then the ARPS curve that you are simulating.
Could you say that again? What kind of wells to consider?
Unconventional part.
Oh, okay, yeah, that's a very good question. So basically we have, we handle both conventional and unconventional, but we use the same formula, the ARPS equation. So the only difference, for example, the unconventional wells might decline faster. So remember the ARPS equation, you have a parameter that control the decline rate. So basically the decline rate of the ARPS equation for unconventional wells would decline faster.
But then you are presuming that for the certain area that you are building the model for?
Yes, so basically we do divide and conquer. So for example, if you only focus on one certain area, for example, Permian only, so basically just check its labors. And we can do that for every local area. Yeah, so
So you're assuming straight away how those wells will be operated, right? They will be operated as the neighbors.
Yeah, so
around.
the big assumption is for example, for the same basin, and then what's going on now can be moved to the future. And the economists, if they don't think the assumption is correct, they can actually override that.
And are you taking completion into account at any time in your model?
Yes, so basically we have a drilling time and also a completion time.
I mean like how you complete those wells, because how you complete them also decides on what your profile of production of those wells will be.
Basically, this is a macro forecast. So we're only more interested in the total production of the United States. So we we do not quite care each single well. So we want to make the total production to be as accurate as possible. So basically, for example, if you are off a little bit at one single well, when you aggregate them, and then maybe one well are a little bit higher, the other a little bit lower. When you aggregate them, so the variance can be quite low. Yeah.
Thank you. Let's thank our speaker again.
Thank you.